Part 8.3, quiz 1, part 3. The last 4 questions from number 7 through number 10. Question number 7. Given a polynomial with 12 terms. Here I said 12 terms. We use the Horner's rule to evaluate at least how many multiplications do we need. Here, this question is designed to check you. So if you can pay attention to the details, What kind of details? All right. First, we know the polynomial we work on written in this way. A0, the constant term, A1x, A2x squared, the last term. All right. In this standard polynomial form, how many terms do we have? The number of terms. Do not use n. So the exact number is n plus 1 terms. N plus 1 terms. The total number of terms. If we use this standard polynomial format. So here, the degree number is n. The degree number, largest degree number plus 1 equals total number of terms. If this number equals 12, then n equals 11, right? N equals 11. And the Horner's rule tells us, based on Horner's rule, n multiplications, right? The degree of the polynomial, n multiplications, right? So put 11 here. Not 12. If we put 12, it's wrong. So 11, not 12. Yeah. All right. So that's one part. Second, why I put this at least. Yeah. Some of you may just ignore it. Yeah. Because I want to make this question solid as possible. Okay? Think about this. Think about, here I give you another polynomial. P of x equals A0 plus A1 x cubed. All right? It's also a polynomial, right? Plus A2 x fifth. How about that? A3 x 10. How about that? A4 x 12. How about that? Right? How many terms do we have if we count? 1, 2, 3, 4, 5. 5. Okay? 5 terms, right? That's how we define the terms, right? 5 terms. Can you say by Horner's rule we can evaluate this by 5 multiplications? We cannot say that, right? More than 5, right? When you do multiplication, you need more than 5 multiplications, right? Yeah. So that's why, to be more precise, I use this at least. At least this many. You may need more than that, right? Yeah. The 12 terms, if we just, we do not use the consecutive power of x, not consecutive, exponent numbers, then you may need more multiplications. So that's the reason. All right, yeah. Number 8. When we apply the linear search on a given array, which of the following types of arrays do we expect to work on? Do we expect? Think about the wording. The wording matters. Yeah, special wording matters. Okay, all right. Although the linear search, we can use it on both unordered array and ordered array, right? But our expectation is unordered array. Our expectation is here. Why here? Why our expectation is here? Because when you design that linear search, you never use the order information. Linear search never use the order information. Never uses the order information, right? So that's the reason our expectation is at the unordered array, that kind of data type. If the input happens to be the ordered array, that's fine. So we treat it as if it is unordered, because we do not take advantage of the order information. Okay? Even there is some important order information there, but this algorithm just designed in that way. Okay? Yeah. So that is the meaning behind this question. Yeah. All right. So next question, number 9. Can we use the worst case efficiency to measure overall efficiency of an algorithm? No. Overall, if you use worst, that's not a good measurement, right? Not a good measurement, because the worst case efficiency usually usually happens in small probability. Small probability, very small. Although you may have it, but that probability is so small, it is very rare to have that worst case. Very rare to have that worst case. Okay? So it is not fair to use that worst case to measure the overall efficiency. Okay? Yeah. Good measurement for overall average case efficiency. So the answer is no. No? Yeah. Average. That's fair, right? Overall average, so you can see, these two words closely related. Okay? All right, so that's number 9. The last question, number 10. Is it possible to show that some algorithm is optimal without exhausting all the algorithms that solve the same problem? Without, okay? Not with, without. We know nobody can exhaust all the possible algorithms. Nobody. Okay, yeah. This question, you need to have our optimality video lecture background. Otherwise, you may not get it. It's hard to imagine. How can you get? Because for an ordinary person, if you ask him or her this question, if they just use their intuition, they may not get it, the correct answer. Yeah, because nobody can exhaust all the algorithms. How can you show, how can you convince people this algorithm is optimal, right? It's hard to imagine that, but we did it in that video. We can show it. We use the example. You need to recall that find the minimum problem. You need to recall that problem as the background. We showed we got an optimal algorithm with n-1 comparisons. We have the convincing arguments to show that. Why we can do that? We couldn't exhaust all the algorithm, but why we can still do that? Reason is very simple. So here, let me give you the reason. All right. The reason is very simple. We get a common property for all the algorithm for this problem. We get that common property. Even we don't know the details of those algorithms, but those algorithms, known or unknown, they must satisfy this property. Okay, so what's that property, right? Yeah, you may ask me, well, what is that common property? So that means, okay, that property, if I express in a simple way, one comparison eliminates one element in the array. Elimination method. One comparison eliminates one element in the array, that property. It is true for all the algorithm for that problem. Okay, yeah. So that is a good example. Only when you have a very good understanding of this minimum of the array problem, then you can get a correct answer. Okay. All right. So let me finish this question and all our quiz 1.